Think about the loudest sound you've ever heard. A thunderclap. A jet engine. A stadium explosion. Now imagine something far beyond all of that. A sound so powerful that it circled the entire Earth multiple times. Yet so low in frequency that no human ear ever heard it. A sound that made the atmosphere itself vibrate for days. Not destruction you can see, but pressure waves racing around the planet at the speed of sound. This is not the sound of Krakatoa reaching people's ears. This is the sound the planet recorded. The infrasonic shockwave that mapped the globe in 1883. To understand the scale of this event, we need to understand the volcano itself. Krakatoa sat in the Sunda Strait between Java and Sumatra, a pressure cooker of tectonic forces. The eruption on August 27, 1883, wasn't a single blast, but a series of 4 cataclysmic explosions. The final one, at 10:02 a.m., was the largest volcanic detonation in recorded history. The energy released was the equivalent of over 200 megatons of TNT, around 13,000 times the atomic bomb dropped on Hiroshima. More than 6 cubic miles of rock and magma were blown into the air. The island itself was obliterated. The audible sound was unimaginable. People in Perth, Western Australia, over 2,000 miles away, heard it as if it were nearby cannon fire. In ships within a 40-mile radius, sailors had their eardrums ruptured instantly. Barometers on nearby vessels shot off the scale. But the greatest scientific revelation wasn't the audible blast. It was what came after. The vast, invisible pressure pulse that traveled around the world. Sound is vibration. Humans hear between 20 and 20,000 hertz. Below 20 hertz, sound becomes infrasound, too low to hear, but still a powerful compression wave traveling through the air. Krakatoa generated an infrasonic wave so immense that it was recorded by microbarographs, early atmospheric pressure sensors, across the entire planet. These instruments weren't designed for violent shock waves. They were weather tools. Yet, after the eruption, their needles suddenly spiked, leaping far beyond normal atmospheric variation. 50 stations across the world, Europe, Asia, Africa, the Americas, all recorded the same pulse. The first pressure wave expanded outward from Krakatoa at around 675 miles per hour, the speed of sound in the warm tropical atmosphere. It spread across oceans, continents, and deserts. Within hours, it had crossed the Indian Ocean. Within a day, it passed through Europe. And after roughly 36 hours, it reached the point directly opposite Krakatoa on Earth's surface, a region near Colombia and the Caribbean. This point is known as the antipode. Now, something remarkable happened. The wave didn't stop. It kept going, now traveling back toward Krakatoa, but from the opposite direction. Microbarographs in London recorded the first pulse, then a second pulse from the opposite direction, then a third and a fourth as the wave continued bouncing around the globe. By the time the atmosphere settled, the infrasonic shockwave had circled Earth at least 4 complete times. Why didn't it simply dissipate? Why didn't this colossal vibration fade away into the sky? 2 scientific breakthroughs came from this event. The first was the acoustic cutoff frequency. The atmosphere doesn't let all sound travel freely. Gravity and temperature gradients act like a filter. Very low-frequency waves are normally weakened or absorbed. But Krakatoa's wave was so powerful that it broke through this natural barrier, demonstrating that extreme events can push infrasonic energy across entire hemispheres. The second breakthrough was even more important: the discovery of the stratospheric waveguide, a massive atmospheric duct that channels infrasound around the planet. The atmosphere isn't uniform. At around 6 to 30 miles above the surface lies the stratosphere, a region where temperature increases due to ozone absorbing sunlight. Because sound travels faster in warmer air, this creates a reflective boundary that bends low-frequency waves back downward. Imagine throwing a stone across a frozen lake. Instead of sinking, it skips. Krakatoa's infrasonic waves skipped between the surface and the stratosphere, trapped and guided like a signal in a planetary-sized fiber optic cable. Without this stratospheric duct, the wave would have faded into space. Instead, Earth's atmosphere acted as a resonating chamber, allowing the pressure pulse to retain its shape and circle the globe repeatedly. The amount of energy inside this inaudible wave was staggering. Atmospheric scientists later calculated that the acoustic energy released during the eruption would have been enough to power human civilization for roughly a year at late 19th century consumption levels. Not as electricity, of course, but in raw mechanical energy contained in the pressure wave. Historical accounts from around the world contain subtle traces of the shockwave's passage. Tiny sea level oscillations measured in tide gauges, unexpected pressure jumps in meteorological logs, and even reports of unusual atmospheric disturbances and high-altitude ripples in cloud formations. The eruption didn't just devastate the region. It forced scientists to rethink the atmosphere itself, not as a static blanket of air, but as a layered, dynamic, acoustically active system capable of carrying signals across thousands of miles. This revelation helped lay the foundation for an entirely new field: global infrasound monitoring. Today, the same principles discovered unintentionally in 1883 are used deliberately by the Comprehensive Nuclear Test Ban Treaty Organization. Their network of more than 50 infrasound stations worldwide can detect nuclear tests on the far side of the planet, monitor volcanic eruptions, track meteors entering the atmosphere, and even measure large explosions in remote oceans. But the modern value of infrasound goes far beyond monitoring nuclear tests. These same low-frequency waves have become a universal diagnostic tool for the entire planet. When a meteor explodes in the atmosphere, like the Chelyabinsk event in 2013, its shockwave generates an infrasonic signature that can be detected across continents, allowing scientists to calculate the object's size, energy, and trajectory, even if it was never seen by cameras. Massive volcanic eruptions also generate infrasonic fingerprints that reveal eruption strength, plume height, and ash content, giving early warnings to aviation networks. Even large storms, atmospheric rivers, and sudden stratospheric warmings produce unique, low-frequency oscillations. Infrasound has quietly become one of the most powerful remote sensing tools ever developed, a way of listening to Earth on a scale far larger than human hearing. And every one of these capabilities traces its scientific lineage directly back to the silent pressure wave of Krakatoa, the greatest sound in human history. A sound no human could hear, yet one that shook the atmosphere for days and revealed the hidden architecture of the sky. If you were captivated by the invisible science of the Krakatoa pressure wave, hit the like button and subscribe. Veil Origins: Impossible Truths.